How do between groups variance and within groups variance influence our ANOVA? Well, the easiest way to understand this is to forget ANOVA altogether and simply look at how we might guess whether or not there are differences between groups based on lots of examples of made-up data. Let's say we have three groups, imaginatively titled Group 1, Group 2, and Group 3. If we're omniscient and know the nature of all things without even needing to collect data, we can look at these groups and say Group 1 comprises a population of mean 10, Group 2 comprises a population of mean 13, and Group 3 comprises a population of mean 10. The variability of these means is called between groups variance. But we're not omniscient, we're scientists. We don't know the underlying population means. We have to make inference about this from the data we collect. But let's also say that we are very, very powerful scientists who are capable of eliminating all within groups variance in our data. That means that if we sample a person from Group 1, their score will be the population mean. Same with Group 2, same with Group 3. There's no need to run an ANOVA to help us with our inferences about the populations. These data are totally unambiguous. We can tell that Group 1 and Group 3 share a population mean of 10, Group 2 has a population mean of 13. We don't even need descriptive statistics. Each data point perfectly describes the population that it's drawn from. Of course, that is a totally unrealistic situation. This isn't how data collection works. Data normally has error, or within groups variance. If we set the population within groups variance so that it's small, a standard deviation of 0.1 for each group, we can generate data that has high between groups variance relative to small within groups variance. Here we can see that our participant data starts to vary about the mean, though it's very easy to see that Group 2 produces data that seem unambiguously different from Groups 1 and 3. The means bear this out too. The other important thing to note is that just like our sample means reflect the population means, our sample dispersions reflect the population dispersions. Not exactly, but if you increase the population standard deviations, the sample standard deviations go up too. We'll see this later on. This is really important because these statistics, the means and standard deviations that we calculate from our observed data, are the only measures of between and within groups variance that we data scientists have. These are the statistics on which we base our ANOVA calculations. Based on all of the above, though, in this case, there's no need to run an ANOVA to know that Group 2 is drawn from a different population to the others. If we generate a few more data sets, we can see that whilst we might see some differences in some experiments, at this ratio of high between groups variance to low within groups variance, it's pretty obvious that one group is drawn from a different population to the others. That is, any ANOVA that we did would definitely be significant. Now, let's take a look at what happens when we increase the within groups variance relative to the between groups variance. I've set things so that in our hypothetical experiments, the standard deviation in each sample has gone up from 0.1 to 2, but the population means are still the same, 10, 13, and 10. The first hypothetical experiment with these population parameters gives us a sign that things might be a bit more ambiguous. The sample means are much more variable, meaning that Group 1's mean is even higher than 12. Remember that under the previous within groups variance, it didn't deviate more than 0.2 either side of 10. That's borne out in the variability we see here. And based on the data we're getting, you can see that we get into territory where we're going to have real trouble determining whether these groups are drawn from different populations or not. Here, we might even get a significant ANOVA for the wrong reasons. The ANOVA here might give us the indication that Groups 2 and 3 are drawn from the same population, but Group 1 is not. You can therefore see how important the ratio of between groups variance and within groups variance is to determining our ANOVA result. In this last set of hypothetical experiments, we've kept within groups variance at the absolute level that it was at, a standard deviation of 2 for each group, but have increased the between groups variance tenfold. The means are 100, 130, and 100. What we see from these hypothetical experiments is that, once again, it's very obvious that group 2 is drawn from a different population to groups 1 and 3. Even with what we would previously have considered large variation in our sample means, we would in all of these cases get significant ANOVA results. This ratio of between and within groups variance is exactly how we calculate the ANOVA F statistic. The bigger it is, the more likely it is that the ANOVA will be significant. It's even more apparent when you plot your data. Between groups variance as the differences in the heights of your bars, and within groups variance as the error bars showing standard deviation around each bar. In this plot, you would definitely expect a significant ANOVA result. But by changing only the within groups variance and therefore the error bars, in this plot you see evidence that the ratio of between to within groups variance is much smaller, and you would therefore not expect a significant ANOVA result. What all of this shows you is that the likelihood that you've got statistically meaningful differences in your data is something you can be looking out for in your data, even before you start running formal statistical tests like analysis of variance.